Alright, so far we've been talking about single charges. Now we're going to progress to what we more naturally use in a lab, which is a wire with current flowing through it. So a bunch of charges moving. So we're going to start with the idea, once again, that force is equal to the charge times the speed or velocity crossed with the magnetic field strength. And then we're going to apply it to a wire. So we're going to start with one charge again and then progress towards multiple charges. So we have a wire that I've looked at some subsection of length L. It has a cross-sectional area, and it's in a magnetic field that is going into the page. That's what an X means. And it has a positive charge, because remember, we follow the electron holes when we talk about current, rather than talking about the direction of the electrons. So electrons would go this way, but we think about things going this way. So using my right hand rule, my fingers would point up. I got my palm down towards my whiteboard, and I'm curling my fingers in to grab the magnetic field vectors going into the page, and so my thumb goes to the left. So we've got our setup where our electric force, or our magnetic force, I should say, goes to the left. Alright, so we don't have to worry about a cross product here. Now notice I've replaced the velocity with the drift velocity. But we don't have to worry about the cross product here because drift velocity goes in the positive y and the b is in the negative z, so they're 90 degrees from each other, so we can just reduce this down without the cross product. Now this only follows one electron hole. We need to deal with every single electron hole flowing, so the current. So I'm going to take that force that we've calculated below and multiply it by every single particle. And we establish how many particles there are by using, so this was particle density times the cross-sectional area times the length. So essentially I'm taking particle per volume times the volume of the wire, so we get the number of particles. So this equals this here, and I've just carried down the magnetic force. Now remember, current is equal to particle density times the fundamental charge times the drift velocity times the cross-sectional area. So a good chunk of this equation gets replaced with the current. So when I write my magnetic force on a current-carrying wire, current-carrying conductor, I take the current times the length of the wire times the magnetic field strength. Now remember, back here we assumed that VD and B were perpendicular. If they're not actually perpendicular, so if our wire was tilted inside of the magnetic field, we would have to do the sign of phi, where phi is the angle between the current, or essentially the length of the wire, and the magnetic field to get the actual magnetic force. So we can write this formula as the force is equal to the current times L, and L is a vector here that points in the same direction as the drift velocity, crossed with the magnetic field strength. And that one would give you the direction out once you do the cross product. And if it isn't a straight wire, so that what I've been talking about so far has been for a straight wire, so if it's not a straight wire, then we do have to do some integration. So this would apply only if the wire is not straight, so non-straight wire.